I don't think it's a well-known fact, but Ford actually has a greater amount of computer processing capability, more than any other auto manufacturer, and certainly only maybe a handful of governments and other institutions have anywhere near our capability.
Computer power doesn't just help operations in the dealership, the office and on the shop floor. Ford's Global Computer Integration Program, using a battery of super machines, is allowing computers across research, engineering and manufacturing to suppliers and information management to communicate with one another in a common language. With this system, Ford can go from design concept to manufacturing work completely on computer screens. And Ford's Puma is a visible sign of this computer concentration. Traditionally, numerous clay models are built to assess the design concept of any new vehicle, but because this car was rendered almost completely on the computer screen, only one single clay was needed to bring it to the design approval stage, faster and less expensive.
Between the design theme and the final product, you can say that the design concept has not been changed. In detail, just very small details, but the general concept is there, and this is what we are very happy about and very proud of.
Computer-aided design, or CAD, is now an established tool in the automotive designer's armory. The traditional practice of rendering early sketches and colored drawings on paper has been replaced by the ability to visualize a three-dimensional and moving form, plus the ability to make instant changes or additions as the concept develops.
In the old process, the nature was that you had sometimes more designers working on one model. Now really you're giving each designer the opportunity to create his own model and to be very consistent then in the design.
The CAD system isn't meant to compromise or supersede any designer's ability. It's a tool to aid creative skills.
The design process changed in the last 10 years quite a lot, theoretically. And I think we can expect to be also quite more radical in the next 10 years.
Under Ford's Global Computer Integration Program, all involved in the vehicle's development will have access to the same database. Under the system already in place, those who style the body and those who devise the mechanicals that go into it share the resource. Using this computer muscle, the product component engineers are able to develop the necessary components to suit that application speedily and efficiently. In the past, numerous prototypes were needed for assessment and physical testing. Under this system, much of the stress analysis is carried out using computer power, with possible weaknesses identified and corrected before the first component is ever produced in metal. Ford also uses computers to design, engineer, and even crash test a vehicle before the company builds its first prototype. About 70% of the crash tests are now carried out on computer, providing more complete and accurate information to ensure a vehicle's crashworthiness as well as to develop future safety systems. Simulated crash tests like these require enormous computer resources, but the results justify the commitment. This is one of the world's most advanced 5-axis milling machines. A team operate and program these machines that transfer computer images into solid models in foam, synthetic wood or traditional clay.
With this milling machine we're able to machine models in either clay or in a harder material like the material looking at here, in a variety of sizes, from something as small as this little tiny model which illustrates the precision of the machine, through to a scale model like this, up to a full-size vehicle.
And no, this is not a new computer game. Ford is the first car manufacturer to use computer simulations to design its vehicle final assembly processes. As manufacturing engineers work alongside project design engineers and use the same computer images of vehicle components and facilities, assembly techniques can now be developed at the same time components are designed. Analysis of past practice shows that this virtual factory not only makes possible the effective reuse of expensive machinery and achieves less changes, but results in processes designed faster and at lower costs.
There are known processes that we have identified that tend to have ergonomic concerns in the past, and we're kind of using that as a best practice to direct our efforts that we're putting into the simulation.
Computer simulations are used here to ensure that, for example, when an operator is assembling a door panel, he or she can complete the work without strain or poor results.
So the idea was to evaluate whether it was feasible for an operator to firstly install the door module assembly and secondly to take the latch part of the assembly, feed it through the door, and with the other hand be able to secure the latch assembly using a power tool. We need to become more analytical, and these tools give us that analytical capability early in the program without having to wait for physical prototypes to be available much later in the program.